There is a temperature so cold that motion itself begins to disappear. Not slow down, not weaken, disappear. Imagine a place where atoms stop vibrating, where time seems to lose its grip, where the very rules of reality begin to blur. Now here's the unsettling question. If everything stops moving, what still remains? Because at what we call absolute zero, minus 273.15 degrees Celsius, physics doesn't just get cold, it gets strange. And maybe it gets incomplete. What happens to light when nothing moves to interact with it? What happens to matter when energy is nearly gone? And more disturbingly, what happens to the universe if it ever reaches that state? Tonight, we're not just exploring the coldest temperature possible. We're stepping into a boundary where science starts to whisper instead of explain. And by the end of this journey, you may realize that absolute zero is not just a number. It might be a doorway, a limit, or something even more unsettling. A place we can approach forever, but never truly reach. So before we begin, if you find yourself drawn to these quiet mysteries of the universe, take a moment to like the video and subscribe to the channel. It helps more than you might think, and it allows us to keep exploring these strange edges of reality together. Now, let's begin with something simple. Temperature. We think we understand it. Hot means fast. Cold means slow. When you heat something up, its particles move faster. When you cool it down, they slow down. It feels intuitive, comforting even. But that understanding only works until it doesn't. Because temperature is not really about how something feels. It's about motion. More precisely, it's about the average kinetic energy of particles. Every atom in your body right now is vibrating, jiggling, moving in tiny, chaotic ways. Even in a solid object like a piece of metal, atoms are never truly still. They're locked in place, yes, but they vibrate, always. Now imagine turning down that motion. Slower, and slower, and slower. Until what? Until they stop? That's the idea behind absolute zero. The point where all classical motion should cease. No vibration, no thermal energy, no movement. But here's where the first crack in reality appears. Because particles never actually stop moving, even at absolute zero. There is always a tiny astatic of motion, a restless flicker, a kind of unavoidable jitter. This is called zero-point energy, and it exists because of something deeply unsettling. The universe does not allow perfect stillness, not because of heat, not because of friction, but because of the fundamental rules of existence itself. This brings us to our first unanswered question. If motion can never fully stop, does absolute zero truly exist? Or is it just a theoretical boundary, like the edge of a map we can draw but never reach? Hold that thought. Because to understand why absolute zero is so strange, we need to look at how close we've actually gotten. Scientists have been chasing this temperature for over a century, and we've come incredibly close, using lasers, magnetic traps, and vacuum chambers. Researchers have cooled atoms to just billionths of a degree above absolute zero. At these temperatures, matter begins to behave in ways that feel almost unreal. Atoms stop acting like individual particles and start acting like a single entity, a unified wave. This state is known as a Bose-Einstein condensate. And when it forms, something extraordinary happens. Imagine a group of dancers moving randomly across a stage. Now imagine they suddenly synchronize, moving as one perfect fluid motion. That's what atoms do at near absolute zero. They lose their individuality. They merge into a single quantum state. It's not just cold, it's collective. But here's the unsettling part. In this state, the distinction between one and many begins to blur, which raises another question. If matter can lose its identity at extreme cold, what does that say about the nature of individuality itself? Is separateness just an illusion, maintained by energy and motion? Or does something deeper define what it means to be one thing? We won't answer that yet, because there's another layer to this mystery. As temperatures approach absolute zero, time itself seems to behave differently. Not in the science fiction sense, but in a subtle, almost philosophical way. Time, as we experience it, is tied to change, movement, events. But if motion slows to nearly nothing, what does time measure? If nothing happens, does time still pass? Or does it become meaningless? This leads to our second unanswered question. At absolute zero, does time lose its meaning? Or does it continue quietly, even when nothing changes? We'll come back to that. But first, let's address something even more surprising. Absolute zero is not just hard to reach. It may be fundamentally impossible. This isn't just a technical limitation. It's a law of physics. The third law of thermodynamics tells us that no system can reach absolute zero in a finite number of steps. No matter how advanced our technology becomes, no matter how clever our methods, we can only get closer, infinitely closer, but never arrive. It's like trying to reach the horizon. Every step brings you nearer, but the distance never fully disappears. Which brings us to a deeper, more unsettling thought. Why would the universe set a limit that cannot be crossed? Why define a temperature that cannot exist in reality? Is it simply a boundary of our equations, or a reflection of something deeper about the nature of existence? Because if absolute zero is unreachable, then the idea of perfect stillness, perfect order, perfect silence may also be unreachable. And that has consequences far beyond physics. It suggests that the universe is never truly at rest, that there is always some level of activity, some irreducible motion, a kind of cosmic restlessness that cannot be eliminated. And that leads us to the third question we've been quietly building toward. If the universe can never be completely still, what is driving that eternal motion? What is it that refuses to stop? Energy? Quantum uncertainty? Or something even more fundamental that we don't yet understand? We're not going to answer that just yet. Because to get there, we need to go deeper. Much deeper. In the next part, we'll explore what happens to light near absolute zero, why superfluids can climb walls, and how emptiness itself may not be empty at all. And somewhere along the way, we might begin to see that absolute zero is not just about cold. It's about the limits of reality itself, and what lies just beyond them. Now, imagine light entering a world where almost nothing moves, not slowing down. Light itself doesn't really slow in the traditional sense, but everything it interacts with does. And that changes everything, because light is not just something that travels, it's something that interacts. It gets absorbed, reflected, scattered, bent. But what happens when the atoms it depends on are nearly frozen? Here's the strange part. At temperatures approaching absolute zero, materials can become almost perfectly transparent to certain forms of energy. Not because they're empty, but because there's nothing moving enough to absorb that energy. It's like throwing a ball into a crowd and realizing the crowd has become statues. Nothing reacts. Nothing catches it. The ball just keeps going. This leads to a quiet, almost eerie thought. If matter stops interacting, does it become invisible to the universe itself? Hold on to that, because this is where things start to feel less like physics and more like something deeper. At extremely low temperatures, certain materials enter a state called superconductivity. In this state, electrical resistance drops to zero, completely. Electric current can flow forever without losing energy. Imagine a loop of wire carrying electricity endlessly, without decay. No heat, no friction, no loss. It's as if energy finds a perfect path and never lets go. But here's the twist. This only happens because the electrons, the particles carrying that current, stop behaving like individuals. They pair up, they move together, perfectly coordinated, no collisions, no randomness, just smooth, uninterrupted motion. Now think about that. At higher temperatures, More energy means more chaos. But at lower temperatures, less energy creates more order. And not just order, cooperation. Which raises a subtle but powerful question. Is chaos the default state of the universe? Or is it something that only appears when energy is high? Because near absolute zero, the universe seems to prefer harmony. Not disorder, not randomness, but unity. We're not going to answer that yet, because something even stranger happens when we go colder. Much colder. There exists a state of matter known as a superfluid, and this is where reality starts to feel almost impossible. A superfluid can flow without viscosity. That means no resistance to flow at all. If you pour it into a container, it doesn't just settle at the bottom. It climbs the walls, it escapes. It forms thin films that creep upward, defying gravity in slow, silent motion. Imagine water, calmly deciding to leave its glass and crawling up the sides, like it has intention. But it doesn't. It's simply following the rules of quantum mechanics, rules that only reveal themselves at extreme cold. Now here's the unsettling part. In a superfluid, all the particles share the same quantum state, just like in a Bose-Einstein condensate. They behave as one, which means you can't really describe one part of the fluid without describing all of it. It's no longer a collection of particles, it's a single, unified entity. This brings us back to one of our earlier questions, but now it feels heavier. If individuality disappears at extreme cold, what does that say about identity itself? Are we only separate because we are warm? Because we are full of energy, constantly moving, constantly colliding? And if that motion were removed, would we also merge into something larger? We're going to leave that question open, because there's another layer, even deeper than this. Let's return to the idea of emptiness. At first glance, absolute zero might seem like the closest thing to nothing the universe can offer. No heat, no motion, no activity. But this is where things become quietly unsettling. Because even in a perfect vacuum, even at temperatures infinitesimally close to absolute zero, there is still something. Fluctuations. Tiny, unpredictable changes in energy. Appearing and disappearing. Particles that briefly exist, then vanish. This is not theory in the abstract sense. It's something we can measure, something we can observe indirectly. The vacuum is not empty. It's alive with possibility. This phenomenon is known as quantum fluctuation, and it suggests something deeply counterintuitive. Nothingness may not be possible. Even when you remove everything you can, something remains. A restless background, a kind of cosmic whisper that never fully goes silent. Now think about what that means. If absolute zero represents the lowest possible energy state, and yet there is still activity, still motion, still fluctuation, then the idea of complete stillness may be an illusion. Not just difficult to achieve, but fundamentally impossible. Which brings us back to our first question, but now it feels sharper. If motion can never fully stop, does absolute zero truly exist? Or is it simply a concept, a boundary we define? But reality refuses to honor completely, and there's another layer to this. Because these quantum fluctuations don't just sit quietly in the background, they can have real, measurable effects. For example, when two perfectly smooth metal plates are placed extremely close together in a vacuum, they are pulled toward each other. Not by gravity, not by magnetism, but by the energy of the vacuum itself. This is known as the Casimir effect, and it reveals something astonishing. Empty space has structure. It has energy. It can exert force. Which raises a new question, one that feels almost philosophical. If even nothingness has energy, what does zero truly mean? Is it a number? A limit? Or something we invented to describe a state that reality never actually reaches? We're not answering that yet, because there's still one thread we haven't fully pulled. Time. Earlier, we asked what happens to time when motion slows down. Now we can go deeper. Because at near absolute zero, processes slow dramatically. Chemical reactions nearly stop. Atomic transitions become rare. Everything stretches out. If you were to observe such a system, it might appear frozen in time. But here's the key insight. Time itself doesn't stop. Only change does. And without change, time becomes difficult to detect. It's like listening to a clock that no longer ticks. Is time still passing? Or has it become meaningless? And this leads us to a more refined version of our second question. Is time something that exists independently, or is it simply a measure of change? Because if it depends on change, then at absolute zero, time might not disappear, but it might become invisible. And that's a very different kind of mystery. Now, we've opened several threads. We've seen that light behaves differently when matter stops moving, that electrons can flow forever without resistance, that fluids can climb walls, that emptiness is not empty, and that time may lose its meaning when nothing changes. But all of this is still happening near absolute zero, not at it, because we still haven't reached that final boundary. And in the next part, we're going to push even closer. We'll explore what happens to entropy, why absolute zero represents perfect order, and why that idea might contradict the very nature of the universe. And somewhere in that contradiction, we may begin to see that absolute zero is not just a limit of temperature, but a limit of understanding itself. Now, let's move closer to something that feels almost philosophical, but is actually one of the most fundamental ideas in physics: entropy. You've probably heard of it before. It's often described as disorder. But that's only part of the story. Entropy is really about how many different ways something can exist, while still appearing the same on the surface. Imagine a neatly stacked deck of cards. There is only one way for it to be perfectly ordered, but there are countless ways for it to be shuffled. That's entropy. Order is rare. Disorder is overwhelmingly more likely. And this idea governs everything, from melting ice, to aging, to the evolution of the universe itself. Things tend to move from order to disorder, from structure to randomness, from low entropy to high entropy. It feels almost like a rule of reality, an arrow, a direction, a kind of inevitability. Now here's where things start to feel strange again, because absolute zero represents the lowest possible entropy, a state of perfect order. Only one possible configuration. No randomness, no alternatives. Everything exactly as it must be. But wait, that seems to contradict everything we just said. If the universe naturally moves toward disorder, why would it even allow a state of perfect order to exist? And more importantly, what would that state actually look like? Let's slow this down. At higher temperatures, particles move more, they collide, they exchange energy, they explore different arrangements. That's what creates entropy. But as temperature drops, motion decreases. Collisions become rare. The number of possible arrangements shrinks until, theoretically, at absolute zero, there is only one arrangement left. No movement, no variation, no uncertainty, a frozen configuration of reality. It sounds almost peaceful. But here's the uncomfortable truth. Perfect order is not just rare, it's fragile. Because the moment any energy is introduced, even the tiniest amount, the system begins to change. Possibilities return, entropy increases. Which means absolute zero is not just difficult to reach, it's unstable in principle, a kind of knife-edge state, where even the smallest disturbance breaks the illusion of perfection. Now think about this. If absolute zero corresponds to perfect order, and perfect order cannot be maintained, then perhaps the universe is fundamentally biased against perfection. Not because it's impossible to imagine, but because it cannot survive. Which leads us to a deeper question. Is disorder not just common, but necessary? Is entropy not just a tendency, but a requirement for reality to exist as we know it? We're not answering that yet, because there's another layer to entropy. one that connects directly to time. Earlier, we asked whether time depends on change. Now we can refine that. Time seems to move in the direction of increasing entropy, from order to disorder, from past to future. This is known as the arrow of time, and it's one of the most mysterious aspects of physics, because most physical laws don't care about direction. They work the same forward and backward, but entropy does care. It gives time a direction, a flow. Now imagine reaching absolute zero. Entropy is at its minimum. There is no lower state, no further direction to go. So what happens to the arrow of time? Does it stop? Does it lose its meaning? Or does it point somewhere else entirely? This sharpens our second question even further. If entropy defines the direction of time, what happens when entropy can no longer change? We'll leave that open, because there's something even more subtle hiding beneath this idea. Let's talk about information. Every physical system carries information, the position of particles, their energy, their arrangement. All of it encodes data about the state of the system. Now here's the interesting part. Entropy is closely related to information. High entropy means many possible configurations, which means less specific information about the system. Low entropy means fewer configurations, which means more precise information. At absolute zero, where there is only one possible configuration, the system is perfectly defined. Maximum information, minimum uncertainty. It sounds like the ultimate clarity, but there's a paradox here, because quantum mechanics tells us that uncertainty can never fully disappear. There are always limits to how precisely we can know certain properties. This is the Heisenberg uncertainty principle. It's not about measurement errors, it's about reality itself. Certain things simply cannot be known simultaneously with perfect precision. So now we have a tension. Absolute zero suggests perfect order, perfect information. But quantum mechanics insists on fundamental uncertainty. Both cannot be fully true at the same time. Which leads to a new question. Is absolute zero incompatible with the deepest rules of quantum reality? Or is our understanding of order incomplete? We're not resolving that yet, because there's another perspective we need to consider. Let's zoom out, far beyond laboratories, beyond Earth, beyond even our galaxy. What happens to the universe itself over time? As stars burn out, as energy spreads, as everything becomes more uniform, the universe moves toward a state of maximum entropy, a state sometimes called heat death. In that future, there are no temperature differences, no gradients, no usable energy. Everything is evenly distributed. Cold, dark, still. At first glance. Hey, that might sound similar to absolute zero, but it's not, because heat death is a state of maximum entropy, complete disorder, while absolute zero is a state of minimum entropy, perfect order. They are opposites, and yet both represent a kind of stillness, a kind of end, which raises a haunting possibility. Could the universe begin in perfect order and end in perfect disorder? Or is there something deeper connecting these two extremes? We're not answering that yet, because there's one final thread in this part, and it might be the most unsettling of all. Let's return to the idea that absolute zero cannot be reached, not just in practice, but in principle. If that's true, then perfect order is not just unstable, it's unattainable, which means the universe is always, at least slightly, imperfect, always carrying a bit of uncertainty, a bit of motion, a bit of unpredictability, and maybe that's not a flaw. Maybe that's the feature that allows everything else to exist, because without that tiny aesthetic of motion, there would be no change, no interactions, no complexity, no life. So here's the quiet thought to carry forward. What if the impossibility of absolute zero is the very reason the universe is alive? We're going to leave that hanging, because in the next part, we'll explore how close we've come to breaking this limit. What happens when scientists try to cheat the laws of thermodynamics, and whether there are loopholes hidden deep within quantum physics itself. And somewhere in that exploration, we may begin to see whether absolute zero is truly forbidden, or simply waiting, at the edge of something we don't yet understand. Now, what if the limit we've been talking about is not as absolute as it sounds? What if, under certain conditions, physics itself seems to bend just enough to let us get closer than we thought possible, or even stranger? What if there are systems that behave as if they've gone below absolute zero? That sounds impossible, because absolute zero is supposed to be the lowest temperature. You can't go lower than the lowest, right? But here's where things begin to feel almost like a loophole hidden inside reality. Scientists have created systems where temperature becomes negative. Not colder than absolute zero in the usual sense, but something far more counterintuitive. To understand this, we need to rethink what temperature really means. Earlier, we said temperature is related to the average energy of particles, but more precisely, temperature is about how energy is distributed. In most systems, particles can have a wide range of energies, from low to very high. And as you add energy, temperature increases. Simple. But in some carefully controlled quantum systems, there's a limit, a maximum energy state. Particles can't just keep gaining energy forever. There's a ceiling. Now imagine this. Instead of most particles sitting in low energy states, you somehow push them into the highest possible energy states. You invert the system. More particles at high energy than at low energy. At that point, the mathematical definition of temperature flips, and the system is described as having a negative temperature. Here's the shocking part. Negative temperatures are not colder than absolute zero. They are actually hotter than infinity. Yes, hotter than any positive temperature. Because if you placed a negative temperature system next to any normal system, heat would flow out of the negative temperature system. It would behave as the hottest thing imaginable. Now pause for a moment, because this breaks our intuition completely. We've been thinking of temperature as a straight line, hot to warm to cold to absolute zero. But reality is more like a loop. Once you reach the highest possible energy distribution, you don't go higher. You flip into a different regime entirely, which raises a fascinating question. If temperature can wrap around like this, is absolute zero truly an endpoint, or just one boundary in a much stranger structure? We're not answering that yet, because there's something even more subtle happening here. These negative temperature systems only exist under very specific conditions. They are isolated, carefully controlled, and they don't behave like everyday matter, which means they don't violate the third law of thermodynamics. They don't actually cross absolute zero. They go around it in a different dimension of behavior. But still, the existence of such systems hints at something deeper. It suggests that our simple picture of temperature may be incomplete. Now let's return to the idea of reaching absolute zero. If it's impossible in finite steps, scientists have become incredibly creative in trying to get as close as possible. They've developed techniques that feel almost like science fiction. Laser cooling, where atoms are slowed down using carefully tuned light. Magnetic traps, where particles are suspended in fields, isolated from the outside world. Evaporative cooling, where the most energetic particles are allowed to escape, leaving the rest colder behind. Each step removes a little more energy, a little more motion. But here's the catch. Every time you get closer, it becomes exponentially harder to go further. It's like trying to remove the last drop of water from a surface, or trying to silence the final whisper in a quiet room. There's always something left. And the closer you get, the more effort it takes to remove even less. Which brings us back to that haunting idea. You can approach absolute zero forever, but you can never arrive. Now here's where things take another turn, because some physicists have asked a bold question. What if, instead of trying to remove all energy, we redefine what we mean by ground state? In quantum mechanics, the ground state is the lowest possible energy state of a system. But what if there are hidden structures, hidden layers, where what we think is the lowest state is not truly the bottom? This idea connects to something known as vacuum energy, the energy of empty space itself. Even when all particles are removed, even when temperature is as low as possible, the vacuum still contains energy, 0-point energy, which means absolute zero does not correspond to zero energy. There is always a baseline, a floor that cannot be removed. Now think about what that implies. If there is always some irreducible energy, then nothing is not truly nothing, and zero is not truly zero. Which brings us back to one of our deepest questions. If the universe never allows complete emptiness, what is the true lowest state of reality? We're still not answering that, because there's one more twist in this part. And it might change how you think about limits entirely. Let's imagine, just for a moment, that absolute zero could be reached. What would actually happen? All motion stops. All entropy is minimized. All systems settle into a single configuration. At first, it sounds stable, final, complete. But here's the problem. Quantum mechanics doesn't allow complete stillness. If particles had exactly zero motion, their position and momentum would be perfectly defined. And that violates the uncertainty principle. So something would have to give. Either our understanding of quantum mechanics breaks down, or absolute zero cannot exist as a physical state. This is not just a technical issue. It's a fundamental tension between two pillars of physics, thermodynamics and quantum mechanics. And we don't yet have a complete theory that fully reconciles them at this boundary, which means absolute zero sits at the edge of our understanding, a place where our best theories start to disagree. Now let's bring everything together for a moment. We've seen that. Temperature can behave in non-intuitive ways. Systems can appear to go beyond traditional limits. Energy can never be fully removed, and quantum mechanics prevents perfect stillness. All of this points to a single, unsettling idea. Absolute zero may not just be unreachable. It may be undefined, in a deeper sense. Not because we lack the technology to reach it, but because reality itself refuses to fully define it. And that leaves us with a powerful question to carry forward. Are the limits we encounter in physics true boundaries of the universe, or signs that our understanding is incomplete? We're going to keep that question open, because in the next part, we'll explore what happens to matter itself as we push toward these extremes. How quantum behavior begins to dominate everything, and whether the concept of temperature even makes sense anymore at the smallest scales. And somewhere in that exploration, we may begin to see that absolute zero is not just a destination we can't reach, but a clue, pointing toward a deeper layer of reality we've only just begun to glimpse. Now, let's ask a quieter question. What happens when temperature stops being a useful idea? Because everything we've talked about so far relies on one assumption. That temperature is a meaningful way to describe a system. But as we move closer and closer to absolute zero, that assumption begins to break. Not dramatically, not all at once, but subtly, quietly, until one day, it simply no longer works. Here's why. Temperature, at its core, is a statistical concept. It only makes sense when you have many particles moving in many different ways, with energy distributed across a wide range. It's an average, a summary, a kind of shortcut. But what happens when all particles begin to behave the same way? When they collapse into a single quantum state? You see, when there is no longer a distribution to measure, at that point, what exactly are we averaging? This is where the concept of temperature starts to dissolve. Not because it's wrong, but because it no longer applies. It's like trying to describe the color of something in a world without light. The language still exists, but the meaning is gone. This brings us to a subtle but powerful idea. Temperature is not fundamental. It's emergent. It only appears when systems are complex enough, chaotic enough, diverse enough, and near absolute zero. That complexity disappears. Everything simplifies. Everything aligns. Everything becomes one. Now here's where things take a strange turn. Because when systems enter this ultra-cold regime, quantum effects don't just appear, they dominate. In our everyday world, quantum behavior is hidden, washed out by noise, blurred by motion. But as temperature drops, that noise fades, and the underlying quantum nature of reality becomes visible. It's like lowering the volume of static until you finally hear the signal underneath, and that signal is deeply unfamiliar. Particles stop behaving like tiny objects. They become waves, not metaphorically, literally. Their position becomes uncertain, their identity becomes shared, their behavior becomes probabilistic. Now imagine this. Instead of thinking of an atom as a tiny ball, think of it as a cloud, a spread out possibility, and at extremely low temperatures. These clouds begin to overlap, merge, interfere, until you can no longer tell where one ends and another begins. This is not just strange. It challenges one of our most basic intuitions, that objects are separate, distinct, independent, because at this scale, they're not. Which brings us back to one of our earlier questions, but now it feels unavoidable. If separateness disappears at low energy, is individuality something that only exists in warmer, de-Noisier conditions? Are we separate because we are chaotic, because we are full of motion? And if that motion were removed, would the boundaries between us dissolve? We're not answering that yet, because there's another layer to this transformation. Let's talk about measurement. In classical physics, you can measure something without fundamentally changing it. You can observe without interfering. But in quantum mechanics, measurement is not passive. It's active. The act of observing a system changes it, collapses possibilities into outcomes. Now here's where it gets interesting. At very low temperatures, systems become extremely sensitive. Because there's so little energy, so little noise, even the smallest interaction can have a huge effect. Which means the act of measuring a near zero system can significantly disturb it. You can't just look at it without changing it. This creates a kind of paradox. To understand what's happening near absolute zero, we have to observe it. But the moment we observe it, we alter it, which raises a deep question. Is there a limit to what we can truly know about the coldest states of reality? Not because we lack tools, but because the act of knowing itself interferes? We'll leave that open, because there's something even more subtle happening beneath this. Let's return to energy. Earlier, we said that even at absolute zero, there is still 0-point energy, a minimum level that cannot be removed. Now imagine zooming in on that energy. What does it actually do? It creates fluctuations, tiny movements, even when everything else is still. It's like a perfectly calm ocean that still has microscopic ripples you can't eliminate. Now here's the key insight. These fluctuations are not random in the usual sense. They are required, built into the structure of reality, which means even in the most ordered, most frozen state imaginable, there is still a kind of hidden activity, a background hum, a quiet instability, and that leads to a new perspective on absolute zero. It's not a place of perfect stillness. It's a place where only the irreducible motion remains, the minimum activity the universe allows, nothing more, nothing less. Now think about what that means. If we strip away all thermal motion, all classical behavior, all randomness, what we're left with is not nothing. It's the foundation, the baseline, the raw layer of reality itself. And that layer is quantum. Which brings us to a powerful idea. Absolute zero is not the absence of physics. It's the exposure of its deepest level. We're not removing reality. We're revealing it. But here's where things become even more intriguing. Because at this level, some of our most familiar concepts begin to lose meaning. Temperature fades, individuality blurs. Even the distinction between particle and wave dissolves. And that raises a profound question. If our basic concepts stop working at the lowest energies, are they truly fundamental, or just approximations that only apply when certain conditions? We're not answering that yet, because there's one more thread we need to follow. Let's imagine trying to build a device that operates near absolute zero. A computer, for example. At first, it sounds ideal. No thermal noise, no random disturbances, perfect stability. But in reality, it becomes incredibly difficult. Because without thermal energy, systems become rigid, transitions become rare. It's like trying to run a machine in a world where nothing wants to move. Even information processing requires change, requires energy differences, requires motion, which means at absolute zero, computation itself might become impossible. And that leads to a fascinating thought. Is a small amount of imperfection actually necessary for systems to function? For information to flow? For anything to happen? We're going to leave that open. Because in the next part, we'll explore how these ultra-cold states are used in real technology, from quantum computers to precision measurements, and how pushing toward absolute zero might unlock entirely new ways of interacting with reality. And somewhere in that exploration, we may begin to see that absolute zero is not just a limit, but a tool, a way of peeling back the layers of the universe until only the deepest truths remain. Now, let's step out of theory for a moment and into something surprisingly real. Because everything we've been talking about is not just abstract physics. It's already being used, right now, in laboratories around the world. And the closer we get to absolute zero, the more powerful these systems become, but also the more fragile and the more mysterious. Let's begin with something that sounds almost futuristic, but already exists. Quantum computers. Unlike classical computers, which use bits that are either 0 or 1, quantum computers use qubits. And qubits don't just sit in one state, they exist in superpositions, both 0 and 1 at the same time. At least, until you measure them. Now here's the crucial detail. Qubits are incredibly sensitive. Any interaction with the environment, any stray heat, any tiny vibration can destroy their quantum state. This is called decoherence. It's like trying to keep a soap bubble intact. In the middle of a storm, which is why quantum computers are cooled to temperatures incredibly close to absolute zero. Not because cold is convenient, but because it's necessary. At these temperatures, thermal noise disappears, random motion fades, and the delicate quantum states have a chance to survive. But here's the twist. Even near absolute zero, they don't last forever. Eventually, interaction creeps in, energy leaks, the system collapses, which raises an important question. If even near-perfect stillness can't preserve quantum states indefinitely, is there a fundamental limit to how long information can exist? We'll come back to that, because quantum computers are just one example. Let's look at something else. Precision measurement. At extremely low temperatures, we can measure things with astonishing accuracy. Tiny changes in magnetic fields, subtle shifts in energy, minute variations in time. Because when thermal noise is removed, even the smallest signals stand out. It's like trying to hear a whisper. In a noisy room, it's impossible. But in complete silence, it becomes clear. This has allowed scientists to build some of the most precise instruments ever created. Atomic clocks, so accurate they would lose less than a second over billions of years. Sensors, capable of detecting gravitational waves. Devices that can measure forces so small, they almost defy imagination. But here's the deeper insight. All of this precision comes from approaching a limit, not reaching it. Because if we could reach absolute zero, something strange might happen. The system would become perfectly ordered, perfectly stable, but also perfectly unresponsive. No fluctuations, no transitions, no signals. Nothing to measure, which leads to a paradox. The closer we get to absolute zero, the more sensitive our instruments become. But if we ever reached it, they might stop working entirely, because measurement requires change. And at absolute zero, there is no change left to detect. We're not answering that yet. because there's another fascinating application: superconductors. Earlier, we touched on this idea, but now let's go deeper. When certain materials are cooled below a critical temperature, they lose all electrical resistance, completely. But there's more. They also expel magnetic fields. This is called the Meissner effect. If you place a magnet above a superconductor, it doesn't just fall, it floats. Suspended, locked in place, it looks like magic. But it's not. It's quantum mechanics, on a visible scale. Now imagine what this means for technology. Power lines with no energy loss, maglev trains that float above tracks, medical imaging devices with unprecedented clarity, all made possible by pushing systems toward absolute zero. But again, there's a limit. Superconductivity breaks down if temperature rises even slightly, or if magnetic fields become too strong. It's a delicate balance, which brings us back to a recurring theme. The closer we get to perfect order, the more fragile the system becomes. Now let's shift perspective again, because there's something even more ambitious happening. Scientists are trying to simulate entire quantum systems, using ultra-cold atoms. They trap atoms in grids of light, cool them to near absolute zero, and use them as building blocks to recreate complex physical systems. It's like building a miniature universe, where you can control the rules, adjust interactions, test theories, explore behaviors that would be impossible to study directly. And here's the remarkable part. These systems can reveal new states of matter. New phases, new behaviors, that don't exist in everyday conditions, which raises a powerful question. Are we discovering these states, or creating them? Because if they only exist under extreme conditions, are they part of nature, or part of our manipulation of it? We're going to leave that open, because there's one more layer to explore in this part, and it connects everything we've discussed so far. Fragility. Every system near absolute zero shares one characteristic. It is incredibly sensitive, not just to heat, but to anything. A stray photon, a tiny vibration, a slight electromagnetic disturbance, all of it can disrupt the system. Which means, to study these states, we have to isolate them, protect them, shield them from the rest of the universe. In a sense, we have to disconnect them from reality. Now think about that. To understand the deepest layers of the universe, we have to remove them from the universe itself. We create artificial environments where the usual rules are minimized, where noise is eliminated, where only the essential behavior remains. And that leads to a subtle but profound question. Are we observing nature as it truly is, or as it behaves when we isolate it? Because if the conditions required to reveal these states do not exist naturally, then what are we really learning? We're not answering that yet, because in the next part, we're going to explore whether absolute zero might actually exist somewhere in the universe, naturally, without human intervention, in the coldest regions of space, in the shadows between stars, or perhaps in places even more extreme. And somewhere in that exploration, we may begin to see whether absolute zero is truly just a theoretical limit, or a hidden reality, waiting quietly in the darkest corners of the cosmos. Now, let's leave the laboratory behind and step into the quietest places in the universe. Because if absolute zero cannot be reached by us, maybe, just maybe, it already exists somewhere out there, far from stars, far from galaxies, in regions so empty, so dark, that almost nothing happens at all. At first, this seems reasonable. Space is cold, extremely cold. The average temperature of the universe today is about 2.7 Kelvin, just a few degrees above absolute zero. This faint warmth comes from something ancient, the afterglow of the Big Bang, a soft radiation filling all of space. No matter where you go, it's there, which means even the emptiest regions of the universe are not completely cold. They are bathed in this faint, persistent energy. Now pause for a moment, because this already tells us something important. Even the universe itself cannot cool all the way down. There is always a background, a minimum temperature, a kind of cosmic floor, which raises our first question for this part. If the universe is expanding, cooling, spreading out, why hasn't it already reached absolute zero? Why does this faint warmth still remain? We'll come back to that, because there are places in space that get even colder than the average, much colder. One of the most fascinating examples is something called the Boomerang Nebula, a cloud of gas expanding rapidly into space. As it expands, it cools, just like air rushing out of a spray can. And in this case, it cools so efficiently that its temperature drops below the cosmic background, down to about 1 Kelvin, colder than the surrounding universe. It's one of the coldest natural places we've ever observed, and yet, still not absolute zero, still not even close. Which leads to a subtle realization. Even under extreme conditions, nature seems to stop short of that final limit. Now let's go deeper. Because there are places in the universe where energy is not just low, but almost completely absent. Intergalactic voids, vast regions between galaxy clusters, where matter is incredibly sparse, sometimes just a few atoms per cubic meter. Imagine a space so empty that if you stood there, you might go seconds, minutes, without encountering a single particle. In these regions, there are almost no interactions, almost no radiation, almost no activity. If anywhere could approach absolute zero, it would be here. And yet, even these voids are not perfectly cold, because they are still permeated by that faint cosmic background radiation, still touched by the lingering energy of the universe's beginning, which brings us back to our earlier question, but now it feels heavier. Why can't the universe fully cool down? Why does this background radiation persist? The answer lies in time, or more precisely, in the history of the universe. That faint radiation is not being actively produced. It's left over, a remnant, stretching, cooling, but never disappearing. As the universe expands, the wavelength of this radiation increases. Its energy decreases. It becomes colder. But here's the key point. It never reaches zero, because to reach zero, it would need to vanish completely. And that would require something very strange. The complete removal of all energy from everywhere, which, as we've seen, may not be possible. Now let's push this further. Imagine the far future of the universe. Trillions of years from now, stars have burned out. Galaxies have drifted apart. Black holes have evaporated. Everything is dark, cold, still. At that point, the temperature of the universe will be incredibly low, closer to absolute zero than ever before, but still not zero. There will still be faint radiation, still tiny fluctuations, still that irreducible background, which leads to a haunting thought. Even at the end of time, absolute zero may remain out of reach. Now let's connect this to something deeper. Earlier, we talked about quantum fluctuations. The idea that even empty space is not truly empty, that particles can appear and disappear, that energy can fluctuate, even in a vacuum. Now imagine this happening in the coldest regions of the universe, in the deepest voids. Even there, these fluctuations persist, which means even in the absence of heat, there is still activity, still motion, still change, and that reinforces something we've been circling around from the very beginning. Absolute zero is not just difficult to reach. It may be impossible because reality itself refuses to be perfectly still. Now here's where things take a more subtle turn. Because there's another kind of cold in the universe, one that doesn't come from temperature alone. Black holes. At first glance, they might seem like the coldest objects imaginable, regions where nothing escapes, where energy is trapped, where everything falls inward. But surprisingly, black holes have temperature. They emit radiation, very faint, but real. This is known as Hawking radiation, and it means that black holes slowly lose energy over time. They evaporate. Now here's the strange part. The smaller the black hole, the hotter it is, and the larger it is, the colder it becomes. Some of the largest black holes in the universe have temperatures incredibly close to absolute zero, far colder than anything we can create on Earth, and yet still not zero, still emitting, still losing energy. Which raises another question. If even black holes cannot reach absolute zero, is there any physical system in the universe that can? We're not answering that yet, because there's one final perspective in this part. Let's step back and look at the universe as a whole, from the Big Bang to the far future, from hot, dense beginnings to cold, diffuse endings. The universe is cooling, spreading, relaxing, but it never quite arrives. It approaches a limit, but never crosses it. Just like every system we've discussed, from atoms to laboratories to cosmic voids, everything follows the same pattern. Closer and closer and closer, but never there. Which suggests something profound. Absolute zero is not just a property of temperature. It's a universal boundary, a limit built into the fabric of reality itself. And that brings us back to one of our deepest questions. Why does this limit exist? Why does the universe allow us to approach, but never arrive? Is it a constraint, a rule, a safeguard, or is it a clue, pointing toward something deeper? Something we don't yet understand? We're going to leave that question open, because in the next part, we'll explore what absolute zero might mean for life itself, whether any form of structure or consciousness could exist near such extreme conditions, and what happens when the processes that define living begin to slow almost to nothing. And somewhere in that exploration, we may begin to see that absolute zero is not just a physical limit, but a boundary between activity and stillness, between existence and something we don't yet have a word for. Now, let's ask a question that feels a little more personal. What happens to life near absolute zero? Not just atoms, not just energy, but systems that process information, that adapt, that respond, that live. Because everything we associate with life, movement, metabolism, change, depends on energy. And as we approach absolute zero, energy becomes scarce. Motion slows, reactions nearly stop, which raises an unsettling possibility. At extreme cold, does life simply pause, or does it disappear entirely? Let's begin with something familiar. On Earth, life has limits. Extreme heat can destroy it, but so can extreme cold. Freeze a cell, and ice crystals form. They expand. They rupture membranes. They damage the delicate structures inside. At first glance, it seems simple. Cold kills. But that's not the whole story, because some organisms have found ways to survive, not by resisting the cold, but by adapting to it. Certain bacteria, tiny, resilient forms of life, can enter a state where their metabolism nearly stops. They don't grow, they don't reproduce, they don't actively consume energy. They simply persist, waiting, sometimes for years, sometimes longer, until conditions improve. This is called cryptobiosis, a kind of suspended animation, life slowed to almost nothing, but not quite nothing. Now imagine pushing that idea further. What if we could lower the temperature, far beyond anything naturally found on Earth, closer and closer to absolute zero? Would life continue to slow indefinitely, or is there a point where the processes that define life can no longer function at all? We're not answering that yet, because there's another layer to consider. Life is not just about surviving. It's about processing information. Cells communicate. They respond to signals. They maintain order internally, and all of that requires movement. Molecules interacting, proteins folding, energy flowing. At near absolute zero, those processes don't just slow, they almost vanish. Which leads to a deeper question. If a system no longer changes, can it still be considered alive? Or is change itself the defining feature of life? We'll come back to that, because there's something even more intriguing. Let's imagine a different kind of life. Not biological, not based on chemistry as we know it, but something built on quantum states. At extremely low temperatures, quantum coherence can persist. Systems can exist in superpositions, entangled, interconnected in ways that classical systems cannot achieve. Now imagine a structure that uses those properties, that processes information not through chemical reactions, but through quantum interactions. A form of life that only exists in extreme cold, where thermal noise is minimal, where coherence can be maintained. It sounds speculative, almost like science fiction, but it raises a fascinating possibility. Could life exist that depends on low energy rather than high? Life that thrives not in warmth, but in stillness? We're not answering that yet, because there's another perspective. Let's return to time. Earlier, we asked what happens to time when motion slows. Now let's apply that to life. If processes slow down, time, from the system's perspective, also seems to slow. Imagine a being living at temperatures near absolute zero. Its internal processes occur extremely slowly. What feels like a second to it might correspond to years or centuries in our frame. To us, it would appear frozen, inactive. But from its own perspective, it might still be experiencing time, still processing, still existing. And this leads to a subtle but powerful idea. Life near absolute zero might not stop. It might simply move too slowly for us to perceive, which raises a profound question. Is life defined by its speed or by its structure? We're not answering that yet, because there's another challenge: stability. At extremely low temperatures, systems become highly ordered, highly rigid, but also highly sensitive. Even a tiny disturbance can disrupt them. Now think about what life requires. It requires stability, but also flexibility, the ability to maintain structure while adapting to change. At near absolute zero, that balance becomes difficult. Too much order, and the system becomes rigid, unable to respond. Too much disturbance, and the system collapses, which suggests that life might require a middle ground. Not too hot, not too cold. A range where complexity can emerge and sustain itself. But then, why does the idea of life at extreme cold continue to intrigue scientists? Because near absolute zero, something unique happens. Noise disappears, randomness fades, and what remains is pure interaction, pure structure, pure information, which leads to an interesting possibility. Even if life as we know it cannot exist at absolute zero, information might, patterns, structures, arrangements that persist without change. Now here's the unsettling part. If a structure can persist indefinitely, without energy input, without change, is it still alive, or is it something else entirely? A kind of frozen information, a static memory, encoded in the fabric of matter. We're going to leave that open, because there's one more layer to explore in this part, and it connects everything we've been building. Let's imagine the far future of the universe again. Cold, dark, energy spread thin. In that environment, traditional life becomes increasingly difficult. But information, patterns, structures might still persist, extremely slowly, barely changing, almost frozen. Now imagine a civilization adapting to that future, slowing itself down, reducing its energy consumption, stretching its processes over longer and longer timescales to survive in a colder universe. Eventually, approaching a state where activity is minimal, but not zero, never zero. because absolute zero remains out of reach. And that might be the key, because as long as absolute zero cannot be reached, there is always some motion, some energy, some possibility for change, which means there is always a possibility, however small, for life, for activity, for existence. And that brings us back to one of our deepest questions. Is the impossibility of absolute zero what allows life to exist at all? We're not answering that yet. Because in the next part, we'll explore what absolute zero might mean for consciousness itself, whether awareness could persist in such extreme conditions, and what happens when the processes that create experience slow almost to nothing. And somewhere in that exploration, we may begin to see that absolute zero is not just a physical boundary, but a limit on what it means to exist at all. Now, let's move into something even more subtle. Not life, not matter, but experience itself, consciousness. Because if temperature affects motion, and motion affects change, and change defines time, then what happens to awareness? When all of that begins to fade, here's the unsettling thought. If the brain were cooled closer and closer to absolute zero, what would happen to the mind? At first, the answer seems obvious. Brain activity depends on electrical signals. Neurons firing, chemical exchanges, energy flowing. Lower the temperature, and those processes slow. Lower it further, and they begin to fail. Eventually, they stop, which suggests a simple conclusion. No motion, no thought. No activity, no consciousness. But let's pause here, because that answer might be too simple, and possibly be incomplete. Let's start with something we know. Consciousness is not a single event. It's a process, a continuous flow of information. Signals passing through networks, patterns forming, dissolving, reforming. It's dynamic, always changing. Now imagine slowing that process down, not stopping it, just stretching it. A thought that normally takes a fraction of a second now takes minutes, then hours, then years. From the outside, the system appears frozen, inactive, but internally, it might still be functioning, just incredibly slowly. Which raises a fascinating question. If a conscious process slows down enough, does it disappear, or does it simply become undetectable? We're not answering that yet, because there's another layer. Let's think about perception. Everything you experience, sight, sound, touch, depends on change, differences, contrast. Your brain detects variations and constructs reality from them. Now imagine a world where nothing changes, no movement, no variation, no signals. What would perception even mean? If there are no differences to detect, there is nothing to perceive, which leads to a deeper question. Is consciousness possible in a perfectly unchanging system? Or does awareness require contrast, require motion, require time? We'll come back to that, because there's something even more intriguing. Some scientists have explored the idea that consciousness might be linked not just to classical processes, but to quantum ones. Tiny, delicate interactions happening at the smallest scales. If that's true, then extreme cold might not just slow consciousness. It might reveal a different layer of it. Because as we've seen, quantum coherence becomes more stable at low temperatures. Noise decreases. Interactions become more precise. Now imagine a system where consciousness is tied to these quantum states. At higher temperatures, it's overwhelmed by noise, chaotic, fragmented. But as temperature drops, the noise fades, and something else emerges. More coherent, more unified. It's speculative, but it suggests a surprising possibility. Could consciousness become clearer as temperature approaches absolute zero? We're not answering that yet, because there's an immediate problem. Even if quantum coherence increases, there's still a need for interaction, for processing, for change. Without that, there is no flow, no sequence, no experience. Which brings us back to time. Earlier, we asked whether time depends on change. Now we can frame it differently. Does consciousness depend on time, or does it create time through change? Because if consciousness requires a sequence of states, then without change, there is no sequence. And without sequence, there is no experience. Which suggests something profound. At absolute zero, even if a system exists, even if its structure remains, consciousness might not. Not because it's destroyed, but because the conditions for experience no longer exist. We're not settling that yet, because there's another perspective. Let's imagine something unusual. A system at extremely low temperature, but not exactly zero. Just enough energy for minimal change, tiny fluctuations, rare transitions. In such a system, conscious processes might still occur, but at an incredibly slow rate. A single thought could take years. A moment of awareness could stretch across centuries. From our perspective, it would seem like nothing is happening. But from within, there might still be a sense of continuity, which leads to a strange idea. Consciousness might not have a fixed speed. It might scale with the system it exists in. Fast in warm, active systems. Slow and cold, quiet ones. But always tied to change. You're always tied to motion. Which brings us back to our central tension. Absolute zero represents no motion, no change, no transitions. And that creates a boundary. Not just for physics, but for experience itself. Now here's the unsettling thought. If consciousness requires change, and change requires energy, and absolute zero eliminates all available energy, then absolute zero might represent a boundary beyond which experience cannot exist. Not death, not destruction, but something more subtle. The absence of process, the absence of flow, the absence of awareness. And that leads to a deeper question. Is consciousness a fundamental property of the universe, or an emergent one that only exists within a certain range of conditions? We're not answering that yet, because there's one more layer to explore. Let's return to the idea of limits. Throughout this journey, we've seen that absolute zero cannot be reached. Either there is always some astatic of motion, some minimal energy, some fluctuation. Now connect that to consciousness. If there is always some motion, no matter how small, then there is always the possibility of change. And if there is always the possibility of change, then there is always the potential for process, for sequence, for something like awareness, which leads to a quiet but powerful thought. The impossibility of absolute zero might not just preserve motion, it might preserve the possibility of experience itself. We're going to leave that hanging, because in the next part, we'll go even deeper. We'll explore what absolute zero might mean for reality as a whole, whether the universe itself has a kind of ground state, and what happens when we try to imagine existence at the very edge of possibility. And somewhere in that exploration, we may begin to see that absolute zero is not just a physical limit, but a boundary between existence and something beyond it. Now, let's take one more step back. Further than matter, further than life, further even than consciousness. Let's ask something bigger. What does absolute zero mean for reality itself? Because up to this point, we've treated it as a limit of temperature, a boundary of motion. But what if it's something more fundamental than that? What if absolute zero is not just about how things behave, but about what can exist at all? Here's the idea. In physics, every system has something called a ground state, the lowest possible energy configuration, the most stable arrangement, the point where nothing more can be removed. For an atom, it's the lowest energy level its electrons can occupy. For a field, it's the vacuum state. For the universe, that question becomes much harder. What is the lowest possible state of everything? Now here's where things become quietly unsettling. Because even the ground state is not empty. It's not still. It's not silent. It's filled with fluctuations, tiny, unavoidable variations, which means the lowest state of reality is still active, still dynamic, still alive in some sense. This brings us to a subtle but powerful shift in perspective. Absolute zero is not the absence of reality. It's the lowest expression of it, the minimal version, the quietest possible state. That still exists. Now imagine pushing this idea further. If we could somehow remove all energy, not just thermal energy, but even zero-point energy, what would remain? Would space still exist? Would time? Would anything? This is where physics reaches its edge, because our current theories don't allow that state. They don't describe it. They don't even fully define what it would mean. Which leads to a profound question. Is true nothingness even possible? Or is the universe constructed in such a way that something always remains? We're not answering that yet, because there's another angle. Let's think about stability. Ground states are stable. That's what defines them. Systems naturally move toward them. They settle, relax, minimize energy. But here's the strange part. If the entire universe were in its ground state, perfectly stable, perfectly ordered, perfectly still, then nothing would happen. No interactions, no changes, no events, which means no time, no processes, no evolution. In a sense, no universe, as we understand it. This creates a paradox. The ground state is the most stable configuration. But if everything were in that state, there would be no activity, no dynamics, no reality in the way we experience it. Which raises a deep question. Does the universe avoid its ground state in order to exist? We're not answering that yet, because there's something even more subtle. Let's return to fluctuations. Earlier, we said that even the vacuum has energy, that particles can appear and disappear. Now imagine those fluctuations, not as noise, but as the foundation of everything. Tiny variations, giving rise to structure, to particles, to forces, to the entire universe. Some theories suggest that the universe itself may have emerged from such a fluctuation, a quantum event, a transition from one state to another. If that's true, then the ground state is not just a passive background. It's active, creative, capable of generating reality itself, which leads to a fascinating possibility. Absolute zero might not represent the end of everything, but the beginning, a state from which something can emerge. Not through classical processes, but through quantum ones. We're not answering that yet, because there's another layer. Let's consider symmetry. At very low energies, systems tend to become more symmetrical, more uniform, more ordered. But the universe we observe is not perfectly symmetrical. It has structure, variation, differences, which suggests that something broke that symmetry. Something introduced imbalance, and that imbalance allowed complexity to form. Now imagine a perfectly symmetrical state, like what absolute zero might represent. No differences, no gradients, no asymmetry. In such a state, there is nothing to drive change, nothing to create structure, which leads to a subtle conclusion. Imperfection may be necessary for existence. Asymmetry may be the source of everything we see. And absolute zero, as a state of perfect symmetry, might represent a kind of limit, beyond which complexity cannot arise. We're not resolving that yet, because there's one more thread to follow. Let's think about laws. The laws of physics describe how systems behave, how they evolve, how they interact. But these laws themselves are defined in terms of change, forces acting, energy shifting, states evolving. Now imagine a system at absolute zero, no change, no evolution, no dynamics. In such a system, what do the laws of physics do? Do they still apply? Or do they become meaningless in the absence of processes? This leads to a deep and slightly unsettling question. Are the laws of physics fundamental, or are they descriptions of change? And if there is no change, do the laws still exist in any meaningful way? We're not answering that yet, Because now we can bring everything together. We've explored temperature, motion, entropy, life, consciousness, and now reality itself. And at every level, we've encountered the same pattern. Absolute zero is a boundary, a limit, a place we can approach, but never fully reach. And that might not be a coincidence. Because if absolute zero were reachable, if perfect stillness were possible, then many of the processes we depend on would cease. Motion would end. Change would vanish. Time would lose its meaning. Life would stop. Consciousness would fade. Reality, as we know it, would dissolve into something static, something unchanging, something silent. Which leads to one final question for this part. Is absolute zero forbidden, not just by physics, but by the very requirements of existence itself? We're going to leave that question open, because in the next part, we'll explore one of the deepest ideas yet, whether the universe is actually moving away from absolute zero, not toward it, and what that means for the ultimate fate of everything. And somewhere in that exploration, we may begin to see that absolute zero is not just a destination we can't reach, but a direction that reality may never be heading toward at all. Now, let's challenge something we've quietly assumed this entire time, that the universe is cooling down toward absolute zero. It feels intuitive. The Big Bang begins hot, extremely hot, then the universe expands and cools. Stars burn out, energy spreads, everything becomes colder. So naturally, we imagine a future where temperature keeps dropping, closer and closer to absolute zero. But what if that picture is incomplete? What if the universe is not simply cooling down, but doing something far more complex? Let's start with a simple observation. Yes, the universe is expanding. And yes, expansion causes cooling. Radiation stretches, energy becomes diluted, temperature drops. But at the same time, something else is happening. Space itself is accelerating in its expansion. Galaxies are not just drifting apart. They're speeding away from each other, driven by something we call dark energy. Now here's the strange part. As space expands faster, it doesn't just cool things down, it also isolates them. Regions of the universe become causally disconnected. Light can no longer travel between them. Information cannot be exchanged. In a sense, the universe is fragmenting, breaking into isolated pockets. Now think about what that means. Temperature is a measure of shared energy, of interactions, of exchange. But if regions of the universe can no longer interact, what does temperature even mean on a cosmic scale? This leads to our first question for this part. As the universe expands and fragments, does the concept of temperature itself begin to break down? We're not answering that yet, because there's another layer. Let's talk about horizons. In an accelerating universe, there is something called a cosmic horizon, a boundary beyond which we can never see. Not because light hasn't arrived yet, but because it never will. Those regions are moving away from us, faster than light can travel through expanding space. Now here's the key insight. That horizon itself has a temperature, a very small one, but not zero. It emits radiation, similar to how black holes emit Hawking radiation, which means even empty space in an expanding universe has a kind of intrinsic temperature. Now pause here, because this is subtle. Even as everything cools, the expansion of space introduces a new kind of warmth, a baseline, a minimum. Not from matter, not from radiation remnants, but from the structure of space-time itself, which raises a deeper question. Is absolute zero impossible? Not just because of quantum mechanics, but because of the geometry of the universe itself? We're not answering that yet, because there's something even more intriguing. Let's imagine the far future again. But now, with this in mind, galaxies are gone from view. Stars have died. Black holes have evaporated. The universe is dark, cold, empty, but not completely. There is still that horizon, still that faint radiation, still that irreducible background, which means the universe never truly settles into perfect stillness. It approaches, but never arrives. Now here's where things take a surprising turn, because some physicists suggest that the universe might not be heading toward a simple heat death. Instead, it might approach a state called de Sitter space, a kind of equilibrium, defined not by zero energy, but by a balance between expansion and quantum fluctuations. In this state, there is still activity, still randomness, still tiny fluctuations, even in the absence of matter, which leads to a powerful idea. The universe might have a minimum temperature, not defined by absolute zero, but by its expansion, a floor set by the structure of space-time itself. Now think about what that implies. Absolute zero is defined as the absence of thermal motion. But if space-time itself introduces fluctuations, introduces energy, then that absence can never be complete, because the stage itself is never perfectly still. Which brings us back to our central question, but now from a new angle. Is absolute zero impossible? Because the universe itself cannot be perfectly quiet? We're not answering that yet, because there's another perspective to consider. Let's think about direction. We often imagine the universe moving toward equilibrium, toward stillness, toward uniformity. But what if equilibrium doesn't mean stillness? What if it means a balance between opposing processes, expansion and fluctuation, order and randomness, cooling and background energy? In that case, the universe is not heading toward absolute zero. It's heading toward a dynamic balance, a state where change still occurs, but in a different way, a quieter way, a slower way, but not a silent one, which leads to a subtle but important shift. Absolute zero might not be the end state of the universe. It might be a boundary that the universe evolves around but never crosses. Now here's the deeper implication. If the universe never reaches absolute zero, then there is always some energy, some fluctuation, some possibility for change, which means the story never truly ends. Not in the sense of complete stillness, not in the sense of total silence. There is always something happening, even if it's incredibly faint, incredibly rare, incredibly slow, which brings us to one of the most intriguing questions so far. Is the universe fundamentally incapable of ending because it can never reach absolute zero? We're not answering that yet, because there's one more layer to explore. Let's return to the idea of time. Earlier, we connected time to entropy, to change, to motion. Now consider a universe approaching this de Sitter state. Change still exists, but it becomes rare. Fluctuations occur, but infrequently. Processes continue, but over immense timescales. From our perspective, it might look like time has almost stopped, but not quite, never quite, which suggests something profound. Time itself may never fully disappear, because the conditions required to eliminate change can never be achieved. And that brings us back to our deeper thread. Absolute zero is not just about temperature. It's about the possibility of change. And if change can never fully vanish, then absolute zero, as a state of complete stillness, may not exist anywhere in the universe. Not in matter, not in space, not in time. Which leads us to a powerful conclusion for this part. The universe may not be moving toward silence, but toward a quieter kind of motion, a softer kind of activity, a state where everything slows, but nothing ever truly stops. We're going to leave that thought open, because in the next part, we'll explore whether there are theoretical ways to escape this limit, whether advanced civilizations could manipulate energy in ways that approach absolute zero differently, and whether the boundary we've been describing is truly unbreakable or simply a reflection of our current understanding. And somewhere in that exploration, we may begin to see whether absolute zero is a fixed limit or a horizon that moves as our knowledge expands. Now, let's ask a question that feels almost rebellious. What if the limit we've been respecting this entire time could be bypassed? Not broken directly, but approached from a different angle. Because throughout history, every time physics presents a boundary, someone eventually asks, is this truly impossible? Or just impossible with the methods we know? So let's explore that idea. Not recklessly, but carefully. Because when it comes to absolute zero, we're not just dealing with a technical limitation, we're dealing with something deeply woven into the laws of nature. Still, there are hints, subtle ones, that suggest the story might not be as simple as you can never get there. Let's begin with a strange thought experiment. Instead of cooling a system, what if we redefine what it means to be cold? Earlier, we saw that temperature is not just about energy. It's about how energy is distributed, and in certain quantum systems, that distribution can be manipulated, inverted, rearranged. This is how negative temperatures appear, not colder than absolute zero, but existing in a completely different regime. Now imagine extending that idea further. Could there be other regions of temperature, other ways of describing energy, that don't fit into our standard scale? Could absolute zero be less like a wall and more like a coordinate in a larger structure we don't fully understand yet? We're not answering that yet, because there's another direction to explore. Let's think about information. Earlier, we connected temperature to entropy, and entropy to information. Now consider this. If we could perfectly control the information in a system, every particle, every interaction, every state, could we effectively eliminate entropy? Not by removing energy, but by organizing it completely. This idea appears in something called Maxwell's demon, a thought experiment where a tiny observer sorts particles, allowing only certain energies to pass, creating order from disorder. At first glance, it seems to violate the laws of thermodynamics. But deeper analysis shows that the act of observing and sorting requires information processing, and that processing has a cost, which preserves the overall balance. Still, the idea lingers. If information and energy are deeply connected, then controlling one might allow us to influence the other, which raises a fascinating question. Could advanced systems manipulate information in a way that effectively approaches absolute zero without violating physical laws? We're not answering that yet, because there's another layer. Let's consider isolation. To cool something, you have to remove energy, but to remove energy, you usually have to interact with the environment, and interaction always introduces some disturbance, some residual energy. Now imagine a system that is perfectly isolated, completely cut off from the rest of the universe. No incoming radiation, no external interactions, no exchange of energy. In theory, such a system could continue to lose internal energy through carefully controlled processes, approaching absolute zero more and more closely. But here's the catch. Perfect isolation is almost impossible, because even the vacuum, even empty space, is not truly empty. There are always fluctuations, always background interactions, which means there is always a leak, always a connection, always something preventing complete stillness, which brings us back to a familiar pattern. Every path we explore gets us closer, but never all the way. Now let's take a more speculative step. What if advanced civilizations, far beyond our current understanding, develop technologies that operate at these extreme limits, not just cooling systems, but manipulating space-time itself, creating regions where energy is redistributed in ways we can't yet imagine? Could they create environments that behave as if they are at absolute zero, not truly reaching it, but functionally indistinguishable from it? We don't know. But it raises an important idea. There may be a difference between reaching a limit and approximating it so closely that the difference no longer matters. Now here's where things become even more intriguing. Let's return to quantum mechanics. At very low energies, quantum effects dominate, and quantum systems can do things that classical systems cannot: superposition, entanglement, non-local correlations. Now imagine a system engineered to exploit these properties fully, a system where energy is minimized, but quantum coherence is maximized. Such a system might not resemble cold in the traditional sense. It might behave in entirely new ways, which leads to a subtle but powerful thought. Absolute zero might not be a single state, but a boundary between different kinds of physics. On one side, classical behavior. On the other, pure quantum reality. And what we call approaching absolute zero might actually be a transition from one description of the universe to another. We're not answering that yet, because there's one more thread to explore: limits. Throughout physics, limits often signal something deeper. The speed of light, the uncertainty principle, the impossibility of perpetual motion, each one, not just a restriction, but a clue. A sign that our current framework has boundaries. And sometimes, those boundaries point toward new theories, new ways of understanding reality. So here's the question that ties everything together in this part. Is absolute zero a final limit or a doorway? A point where our current theories stop working and something deeper begins? We don't know. But history suggests that every time we reach such a boundary, we're on the edge of discovery. Now let's bring this back to where we started. We've tried cooling systems, manipulating energy, controlling information, isolating environments, exploring quantum behavior, and every path leads us to the same place. Closer and closer and closer, but never quite there, which might be the most important clue of all, because it suggests that absolute zero is not just a technical challenge. It's a structural feature of reality, a limit that defines how the universe behaves, but also a hint that there may be more to understand. And that leaves us with a powerful question moving forward. If absolute zero cannot be reached, what is it really telling us about the nature of reality? We're going to carry that question into the next part, because next, we'll explore one of the most intriguing ideas yet: whether absolute zero is connected to the origin of the universe itself, and what happens when we try to trace reality back, not forward in time, but all the way to its beginning. And somewhere in that exploration, we may begin to see that the coldest point imaginable might also be connected to the moment everything began. Now, let's turn everything upside down. Up until now, we've been moving forward in time, from the hot beginning of the universe, toward a colder future, toward stillness, toward absolute zero. But what if we reverse that direction? What if instead of asking where the universe is going, we ask where it came from? Because there's something strange hiding here. At the beginning of the universe, everything was extremely hot, dense, chaotic, energy packed into a tiny region. But here's the paradox. Despite that chaos, the early universe had very low entropy, highly ordered, highly structured in a subtle way. And that's not what we would expect. High temperature usually means high entropy, disorder, randomness. But the early universe was hot, and yet ordered. Which raises our first question for this part. How can something be extremely hot and still be in a low entropy state? We're not answering that yet, because to understand this, we need to rethink what order means. Entropy is not just about temperature, it's about the number of possible configurations. And in the early universe, despite all that energy, there was a kind of uniformity, a smoothness. Matter and energy were distributed almost evenly. There were no stars, no galaxies, no structures, just a nearly uniform field. And strangely, that counts as low entropy, because gravity hadn't yet had the chance to create complexity, to form clumps, to generate variation. Now here's where things get interesting. As the universe evolves, entropy increases, but not by becoming more uniform, by becoming more structured. Stars form, galaxies emerge, black holes appear, complexity grows. Which means, in a gravitational system, disorder doesn't look like randomness. It looks like structure, which flips our intuition completely. Now connect this back to temperature. The early universe was hot, but ordered. The far future universe is cold, but disordered, which suggests something profound. Temperature and entropy are not always aligned in the way we expect. And that brings us back to absolute zero. Because absolute zero represents minimum entropy. Perfect order. But the early universe was also close to minimum entropy, despite being extremely hot. So here's the unsettling idea. The beginning of the universe and the concept of absolute zero might be connected, not in temperature, but in structure. Both represent extreme states, boundaries, limits. Now let's push this further. Some physicists have proposed that the arrow of time, the direction from past to future, is defined by the increase of entropy, from low entropy to high entropy, which means the reason time flows forward is because entropy increases. Now imagine reversing that, moving backward in time. Entropy decreases, order increases, until we reach the beginning, a state of maximum order. Now compare that to absolute zero, a state of minimum entropy, maximum order. Do you see the connection? Both represent boundaries, where entropy cannot decrease any further, which leads to a fascinating question. Is absolute zero a kind of mirror to the beginning of the universe? We're not answering that yet, because there's another layer. Let's think about energy. At the beginning, energy was concentrated, dense, intense. Now, it's spread out, diluted, cooling. But total energy may not have changed in the way we expect. It's just redistributed. Now imagine compressing the universe again, reversing expansion, bringing everything back together. Energy would increase, temperature would rise, entropy would decrease, which suggests something intriguing. Absolute zero is not just about low energy. It's about the distribution of energy. And the beginning of the universe was also a special kind of distribution. Highly ordered, highly constrained. Now here's where things become even more speculative. Some theories suggest that the universe may not have a single beginning, but cycles, expansions, and contractions, birth and rebirth. In such models, the end of one universe could lead to the beginning of another. Now imagine the transition point between one cycle and the next, a state of extreme conditions, possibly extreme order, possibly something like a ground state of the universe, which raises a bold question. Could absolute zero, or something like it, play a role in the birth of a universe? We're not answering that yet, because there's a deeper issue. Let's return to time again. At the beginning of the universe, time as we understand it may not have existed, or at least it behaved very differently. Now think about absolute zero, a state where change disappears, where motion stops, where entropy cannot decrease further. In such a state, time might also lose its meaning, which suggests a strange parallel. Both the beginning of the universe and absolute zero are states where time breaks down, where our usual concepts no longer apply, which leads to a profound idea. Absolute zero might not just be a limit of temperature, but a limit of time itself. We're not resolving that yet, because there's one more thread to follow. Let's think about possibility. At the beginning of the universe, everything that would ever exist was encoded in that initial state. All structure, all complexity, all future events. In some sense, maximum potential. Now consider absolute zero, a state of perfect order, minimal entropy, no randomness, no variation. At first glance, it seems like the opposite. No potential, no change. But here's the twist. Quantum fluctuations still exist, even in the lowest energy state, which means even at absolute zero. There is still possibility Still uncertainty. Still the seeds of change. Now connect that back to the beginning, a state of low entropy, but full of potential. And suddenly, the difference between beginning and end doesn't seem so clear, which leads to one of the deepest questions so far. Is absolute zero an end point or a starting point? We're going to leave that open, because in the next part, we'll explore whether the universe itself might reset, whether these extreme boundaries connect in ways we don't yet understand, and whether the coldest state imaginable could somehow be linked to the birth of everything. And somewhere in that exploration, we may begin to see that absolute zero is not just a limit, but part of a larger cycle, one that connects beginnings and endings in ways we are only just beginning to imagine. Now, let's follow that idea all the way to its edge. If absolute zero might connect to the beginning of the universe, then we have to ask something even more unsettling. Could the universe somehow reset itself? Not metaphorically, not philosophically, but physically. Because throughout everything we've explored, a pattern keeps appearing. Limits, boundaries, states that cannot be reached, but can be approached indefinitely. Absolute zero, maximum entropy, the beginning of time. All of them sit at the edges of our understanding, and sometimes edges are not endings. They're transitions. So let's imagine this. Far in the future, the universe continues expanding. Galaxies disappear beyond horizons, black holes evaporate, energy spreads thinner and thinner. Everything becomes cold, dark, quiet. Eventually, the universe approaches a state of maximum entropy. No usable energy, no gradients, no structure. Just a thin, uniform distribution of energy and fluctuations. This is often called heat death. But here's the strange part. Even in this state, quantum fluctuations remain. Tiny variations, random events, rare, but not impossible. Now imagine waiting long enough, not billions of years, not trillions, but timescales so vast, they almost lose meaning. In such a universe, even extremely unlikely events become inevitable. Given enough time, fluctuations can create structure again. Particles can briefly assemble. Energy can momentarily concentrate. Now here's where things become truly strange. Some theories suggest that entire regions of space could spontaneously fluctuate into new states, new beginnings, tiny pockets where conditions resemble the early universe. Hot, dense, ordered. In other words, a kind of new Big Bang. Not the same universe restarting, but a new one emerging from the fluctuations of the old. Which leads to a fascinating idea. The universe might not end. It might transform. Now connect this back to absolute zero. Absolute zero represents a state of minimal energy, minimal entropy, perfect order. But it cannot be reached. And the universe never fully settles into maximum entropy either. There are always fluctuations, always residual motion, which means both extremes, perfect order and perfect disorder, are never fully realized. They are approached, but never achieved. And that creates something interesting, a kind of tension, a balance, a space where change is always possible. Now imagine that this balance is what allows cycles to occur, not necessarily in a simple repeating way, but as a continuous process. Fluctuations giving rise to structure, structure evolving, entropy increasing, energy spreading, then fluctuations again. Which raises a powerful question. Is the universe fundamentally cyclic? Not in a predictable loop, but in a statistical sense? We're not answering that yet, because there's another layer. Let's think about memory. If a new universe emerges from fluctuations, does it carry any information from the previous one? Or is it completely independent? At first glance, it seems like it should be independent, random, unrelated. But here's the subtle point. The fluctuations arise from the underlying state of reality, from the vacuum, from whatever ground state exists, which means the properties of that ground state influence what can emerge. So even if individual universes are separate, they may share deeper rules, deeper structures, which leads to an intriguing idea. There might be a continuity, not of events, but of laws. Now connect this back to absolute zero. If absolute zero represents the lowest energy state, the ground state, then it might also represent the foundation from which everything emerges. Not as a final destination, but as a kind of baseline, a canvas. Now here's where things become even more subtle. Earlier, we talked about time breaking down at extreme limits. At the beginning of the universe, time behaves differently. At absolute zero, time may lose meaning due to lack of change. Now imagine a transition between universes, a fluctuation that gives rise to a new beginning. What happens to time at that boundary? Does it continue? Does it reset? Or does it emerge anew? This leads to a deep question. Is time fundamental, or does it emerge from processes within the universe? We're not answering that yet, because there's one more thread to follow. Let's think about inevitability. If fluctuations can create new universes, and if the universe lasts long enough, then such events may not just be possible, they may be inevitable. Given enough time, everything that can happen will happen. Which means new beginnings are not rare, they are guaranteed. Now connect that back to absolute zero. Absolute zero is unreachable, which means there is always some energy, some fluctuation, some possibility. And that possibility is what allows these rare events to occur, which leads to a quiet but powerful realization. The impossibility of absolute zero may be what keeps the universe alive, not in the biological sense, but in the sense of ongoing possibility, ongoing change, ongoing emergence. Now let's bring everything together. We started with a simple idea, the coldest temperature possible, a limit, a boundary. But along the way, it became something more, a connection between motion and stillness, between order and disorder, between beginning and end, and now, possibly, between one universe and another, which leads to one of the deepest questions in this entire journey. Is absolute zero a limit that prevents the universe from ending, or a feature that allows it to begin again? We're going to leave that open, because in the next part, we'll step back one final time and look at everything we've uncovered, to ask a question that ties it all together. What is absolute zero really? Not as a number, not as a temperature, but as a concept, a boundary, a clue, and possibly one of the deepest hints we have about how reality itself is structured. Now, let's slow down. Not the universe, not the atoms, but the way we think about all of this. Because after everything we've explored, absolute zero no longer feels like just a number. It feels like a question, a boundary, a kind of quiet paradox that keeps showing up, no matter where we look. So let's ask it directly. What is absolute zero? Really? At first, it seems simple. The lowest possible temperature, minus 273.15 degrees Celsius, 0 Kelvin, the point where thermal motion disappears. But now we know that description is incomplete, because motion never fully disappears. Quantum fluctuations remain. 0-point energy persists. The universe refuses to be perfectly still. So absolute zero is not a place we can reach, not even a place that fully exists. It's something else, a limit. But not just a physical limit, a conceptual one. Now here's where things become more interesting. In physics, limits often reveal something deeper. The speed of light is not just about how fast things can move. It defines causality, the structure of space-time, the way information flows. The uncertainty principle is not just about measurement. It defines the limits of knowledge itself. And absolute zero may belong in that same category. Not just a boundary of temperature, but a boundary of possibility. Let's unpack that. Temperature is tied to motion. Motion is tied to change. Change is tied to time. And time is tied to experience. So if absolute zero represents the absence of motion, it also represents the absence of change, which means it touches every layer of reality we've explored: physics, entropy, life, consciousness, time. All of them begin to break down as we approach this limit, which suggests something profound. Absolute zero is not just about cold. It's about the edge of process, the edge of anything happening at all. Now here's the strange part. Even though we can't reach it, we can define it precisely. We can calculate it. We can approach it. We can build entire technologies around it. It's like a horizon, always visible, always guiding, but never fully accessible. Which raises a subtle question. Why does the universe allow us to define something that cannot exist? We're not answering that yet, because there's another perspective. Let's think about opposites: hot and cold, order and disorder, energy and stillness. Absolute zero sits at one extreme, but we've seen that the universe never fully occupies extremes. Not perfect order, not perfect disorder, not complete stillness, not total chaos. Instead, it lives in between, in gradients, in transitions, in motion, which suggests that extremes are not destinations. They are references, points that define the space in which reality operates, and absolute zero may be one of those reference points. Now let's connect this to something deeper. Throughout this journey, we've asked three questions. Can motion ever fully stop? Does time exist without change? And what remains when everything else is removed? We never fully answered them, but we circled them from different angles, through physics, through cosmology, through life and consciousness. And each time, we came to the same place. Something always remains. Some motion, some fluctuation, some possibility, which suggests that absolute zero is not a reachable state, because reality itself is built to avoid it, not as a rule imposed from outside, but as a consequence of its structure. Now here's the deeper implication. If absolute zero cannot be reached, then perfect stillness cannot exist. And if perfect stillness cannot exist, then there is always change, always activity, always the potential for something to happen, which means existence is not something that can turn off. It can slow, it can fade, it can become incredibly quiet, but it never fully disappears. And that leads to a quiet but powerful idea. Absolute zero is not the end of motion. It is the point that defines why motion never ends. We're not resolving that yet, because there's one more layer. Let's think about understanding. Every concept we use, temperature, energy, time, is a tool, a way of describing reality. But as we approach extreme limits, those tools begin to fail. They lose meaning. They stop working in the way we expect. And absolute zero is one of those limits, a place where our familiar concepts start to dissolve, which raises a final question for this part. Is absolute zero a property of the universe, or a limit of our understanding of it? Because it might be both, a real boundary, and a sign that we need new ways of thinking. Now let's bring everything together. We started with a simple idea, the coldest temperature possible. But along the way, it became something else, a boundary between motion and stillness, between time and timelessness, between existence and non-existence. And yet, we never actually reach it. We only approach, which might be the most important clue of all, because it suggests that absolute zero is not something the universe contains. It's something the universe points toward, a direction, a limit, a concept that helps define everything else. And that leaves us with one final question to carry into the last part. If absolute zero is not a place we can reach, then why does it exist in our understanding at all? What is it trying to tell us about the nature of reality? We'll explore that in the final part, because next, we'll step back completely and look at this idea one last time, not as a physical limit, but as a clue, a hint, and possibly one of the deepest insights we have into how the universe is structured. Now, Let's return to the question we've been quietly carrying from the very beginning. Not what absolute zero is, but why it exists at all. Because after everything we've explored, it no longer feels like just a scientific definition. It feels intentional. Not in the sense of design, but in the sense of structure. A boundary that appears everywhere, in atoms, in quantum fields, in the vacuum of space, in the fate of the universe itself. And every time we approach it, the same thing happens. Reality doesn't stop. It resists. It softens. It changes behavior. But it never becomes perfectly still. Which leads us to a quiet realization. Absolute zero is not a place in the universe. It is a limit built into the universe. Now here's where everything comes together. We asked 3 questions at the beginning. If motion can never fully stop, what is driving that motion? If time depends on change, what happens when change disappears? And if we remove everything, what remains? Now, after this entire journey, we can begin to answer them. Not with certainty, but with something deeper. Understanding. First, motion never fully stops, because the universe does not allow complete certainty. Quantum fluctuations. Zero-point energy. These are not imperfections. They are foundations. They ensure that something is always happening, even at the lowest possible energy, which means motion is not something added to reality. It is something that cannot be removed from it. Second, time does not disappear, because change never fully disappears. Even in the quietest states, there are still fluctuations, still transitions, still events. And as long as something changes, time has meaning, even if that meaning becomes incredibly subtle, incredibly stretched, almost invisible, but never gone. And third, when we try to remove everything, what remains is not nothing. It is the ground state, the baseline, a restless, fluctuating foundation from which everything else emerges. So now we can say something surprising. Absolute zero is not the absence of reality. It is the closest we can come to seeing reality without its noise, without its chaos, without its complexity. And what we find there is not emptiness. It is structure, subtle, unavoidable, and always in motion. Now here's the deeper insight. Throughout this journey, we kept encountering limits, and each limit did something interesting. It didn't stop us. It revealed something. The speed of light revealed the structure of space-time. The uncertainty principle revealed the limits of knowledge, and absolute zero reveals something just as profound. It reveals that the universe cannot be perfectly still. That existence itself requires a minimum level of activity, a minimum level of uncertainty, a minimum level of motion, which means absolute zero is not just a limit of temperature, it is a limit of possibility. Now let's take one final step back. Imagine a universe where absolute zero could be reached, where motion fully stops, where change disappears, where everything becomes perfectly ordered, perfectly still. At first, it might sound peaceful, final, complete. But look closer. In that universe, nothing would happen. No interactions, no time, no life, no consciousness, no future. It would not be a universe. It would be a frozen state with no way to evolve, no way to change, no way to exist in any meaningful sense. And that's the key. The reason absolute zero cannot be reached may not be a limitation. It may be a requirement, a safeguard, a rule that ensures the universe can never fully shut down. Which leads to one final powerful idea. The impossibility of absolute zero is what keeps reality alive. Not alive in the biological sense, but alive in the sense that something is always happening, always changing, always becoming. Now think about that. Every star that burns, every atom that vibrates, every thought that forms in your mind, all of it exists because perfect stillness is forbidden, because the universe refuses to become completely quiet. And that might be the most important insight of all. Absolute zero is not where everything ends. It is the reason everything continues. Now, before we gently drift out of this idea, there's one last thing. If this kind of quiet exploration, these slow journeys to the edge of reality, help you relax, help you think, or simply make the universe feel a little more fascinating, take a moment to like the video, subscribe to the channel, and maybe share it with someone who enjoys these kinds of questions too. And I'd really love to know, which idea stayed with you the most? Was it the idea that motion never truly stops? That time depends on change? Or that the universe might never fully end? Let me know in the comments. Because sometimes, the most interesting part of these journeys is not the answers. It's the questions we carry with us afterward. And speaking of questions, this one leads somewhere even deeper. Because if absolute zero defines the limit of motion, then what defines the limit of space itself? Is there an edge to the universe? In the same way there is an edge to temperature? Or is that boundary just as unreachable, just as mysterious? That's where we're going next. But for now, just let this thought settle in. Somewhere, in the quietest corners of reality, everything slows. Everything softens. Everything approaches stillness. And yet, something always remains. A tiny flicker, a subtle motion, a quiet reminder that the universe never truly stops.